So we are going to deal with electricity today. Okay, number theory portions matra we'll be seeing only theory portions. Alright, so first and foremost, we are going to see what are the stuff we are going to study in this particular chapter. We are going to see what electricity is, what is static electricity, what is current electricity, what is Ohm's law, what is resistance, what are conductors, what are insulators, what are semiconductors. After which we'll be seeing about heat effect of electricity and also series connection, parallel connection, and all those sorts of things. And we are not going to deal with any problems in this particular session. Maybe sometime during next week we can go ahead and do some problems. All right, I've shared quite a lot of problems with you all. And at least I've shared. Try all those things out. Get up. And doubt Atulya, you have joined. Atulya, yeah. All right. So and share with each other as well. Get a problems share. There will be new kind of problems which teachers will be introducing. If you get exposure to that, it is pretty good. All right. So now coming to electricity. Electricity is, what is electricity? Electricity is basically something to do with charge. So first we have to see what charge is. All right. What is meant by electric charge? How do we know electric charge is present? See, when you rub a foam onto your dry hair, and when you try bringing it here, small pieces of paper, then it gets attracted. Now, what is happening? The comb, the sheet that you are using is going to be neutral. Your paper is also neutral. So, what is going to happen when you rub it onto your dry hair? Something is getting realigned inside. Okay, some kind of charge is getting exposed. All right. So these kind of charges are responsible for creating attraction. So same thing is going to happen with glass rod as well. Same thing is going to happen with glass rod and silk cloth. In case glass rod is rubbed with silk cloth, what is going to happen? The glass rod is going to get a positive charge and silk cloth is going to get a negative charge. All right. So same thing is going to happen when animal fur is rubbed with ebonite rod. Ebonite rod is rubbed with animal fur. All right. So then also the charges are going to appear. These kind of charges which do not move, they are known as static charges. And we know that the charges are of two kinds, which is positive and negative. Now, which one is positive and which one is negative? See, by convention, there is no hard fast rule. By convention, we have been following that whatever charge is acquired by the glass rod when it is rubbed with a woolen cloth. Say this is glass rod and this is a woolen cloth. Okay, and we rubbed it with each other. The charge acquired by the glass rod, is taken as positive. All right. So this is the convention. There is no hard fast rule, but then this has been followed all days. Now, what are the properties of charges? Like charges are going to repel each other, unlike charges are going to attract each other. Most important questions will come from what is a Coulomb? What is unit of a charge? Define 1 Coulomb. Define the unit of charge. What is the unit of power? Define 1 unit of power. What is unit of work? Define 1 unit of work. Such questions are very common. So, please, give special attention to all these things. What is SI unit of electric charge? SI unit of electric charge. Now we have not yet started on with electricity. We are just telling about the charge. Why are we talking about the charge? Because charge has something to do with electricity. If the charge flows, then we say that it is electric current. If the charge stays, then we say that it is static current. All right. So first we have to understand what causes electricity. What is the cause of electric current, right? So SI unit of electric charge is a Coulomb. Okay. So what is 1 Coulomb? What is 1 Coulomb? I'll just show a picture of this first. All right. Say 1 Coulomb. Some amount of charge is there. We don't know if it is 1 Coulomb. Okay. We don't know if it is 1 Coulomb. If a particular amount of charge is there, if the same amount of charge is kept at a distance of 1 meter. Okay. Some amount, we don't know if it is 1 Coulomb. Okay. Some amount of charge is kept equal. 2 equal amount of charge are kept at a distance of 1 meter. And we found that they are experiencing a force of 9 into 10 raised to 9 Newton among each other. They repel or attract with a force of 9 into 10 raised to 9. Then we can say that the amount of charge kept at both places is equal to 1 coulomb. Say some amount of charge is over here and equal amount of charge is kept at a distance of 1 meter from each other, and the force experienced by them is 9 into 10 raised to 9. Then we can say that this amount of charge, the amount of charge is going to be 1 coulomb. The amount of charge is going to be equal to 1 coulomb. Okay, this is one definition that we can give. So we'll go through that definition. All right. So what is 1 coulomb? 1 coulomb is that quantity of charge, is that quantity of electric charge that exerts a force of 9 into 10 raised to 9 on an equal charge which is placed at a distance of 1 meter from it. Which is placed at a distance of 1 meter from it. So this is the definition. This is one of the definitions of Coulomb. All right. So generally the proton charge is taken as plus. All right. This is by convention plus 1.6 to 10 raised to minus 19 coulombs. The electron charge is taken as negative, but it is equal in charge. Negative minus 1.6 into 10 raised to minus 19 coulombs. Okay. This is also an important question. Calculate the number of electrons in 1 coulomb. So how do you do that? Calculate the number of electrons in 1 coulomb. Okay. 1 electron has a charge of 1.6 into 10 raised to minus 19 coulombs. Minus 19 coulombs. Now, what is the number of electrons in 1 coulomb? Chakka has to be written below Chakka itself. Coulomb has to be written below Coulomb itself. What is the number of electrons? What is the number of electron? Cross method. Hope my kids remember this. 1 into 1 divided by 1.6 into 10 raised to minus 19. Okay. So if one chocolate costs 10 rupees, then how many chocolates are you going to get for 100 rupees? How do you do that? Crisscross method. 100 into 1 divided by 10. 100 into 1 divided by 10. Okay. So likewise, but the important point being the rupee has to be written below the rupee itself and chocolate has to be written below the chocolate itself. This method is known as crisscross method. So what did we learn over here? 1 electron has a charge of 1.6 into 10 raised to minus 19 coulomb. So they have asked us what will be the number of electrons in 1 coulomb. Coulomb has to be written below coulomb, and then you apply the crisscross method. 1 into 1 divided by cross. You have to cross multiply and then divide the other person. 1.6 into 10 raised to minus 19. All right. You will get an answer of 6.25 into 10 raised to 18. You have to do multiplication and you have to know powers in order to do that. You don't have time to elaborate on how to do the calculation. So this is one of the definitions of Coulomb. So you can also define Coulomb as this is equal to the charge. 1 coulomb is equal to the charge which is contained in 6.25 into 10 raised to 18 electrons. Say 6.25 into 10 raised to 18 electrons are playing together over here. The charge contained in this particular set is known as 1 coulomb. The charge in this particular set of 6.25 into 10 raised to 18 electron is said to be 1 coulomb. Okay, we are done with coulombs. Now we are going to conductors, insulators, and we have another set which is known as resistors are also there. Semiconductors are also there. What is meant by conductors? Conductors are those which actually allows the electricity to flow through it. Metals are very good conductors. Alloys, on the other hand, alloys have less conductivity as compared to metals. The most important questions are asked from alloys. What element is used to create electric bulb? What element is used to, what alloy is used to create heating elements? All those things, all those questions are generally asked. And why are they being used? Why is nichrome wire used in creating electric bulb? Okay, all these questions we'll be discussing a bit later. Now, what are conductors? Conductors are substances who allow electricity to flow through it. Metals are generally very good conductors. Alloys, on the other hand, have less conductivity. Some of the alloys that we have to learn is nichrome, manganese, constantan. They also do conduct electricity, but they are known as resistors. Why? Because they have comparatively less conduction as compared to metals. Okay. Alloys are generally used to create heating elements. Alloys are generally used to create heating elements. Why? Because anything which resists, say if you are resisting your mother, okay, when she asks you to study, you are resisting your mother, then there is a friction which is created, right? Because of that friction, heat is generated. Likewise, when electricity is flowing, this particular resistor is going to resist the electricity. Any resistance, if you see, that is going to create a heat. So in order to make use of that heat, we use alloys in bulbs, electric bulbs, or iron box, and all those things. Human body is also a resistor because it does not conduct electricity in a very good way. All right. Carbon as graphite also conducts electricity. Carbon as a graphite conducts electricity. Human body is not a very good conductor, but it does conduct electricity. Or like pure water does not conduct electricity. Pure water does not conduct electricity. Dry air does not conduct electricity. But then if you mix pure water, if you take pipe water, that is corporation pipe water, that contains a lot of ions and elements in it, that is a very good conductor of electricity. Humid air is a good, we can't say it is a good conductor of electricity, but it does conduct electricity. Okay, substances which do not allow electricity to flow through it, they are known as insulators. So substances through which electricity cannot flow are known as insulators. Now, how do conductors conduct electricity? See, conductors, if you see, they are generally metals, right? These metals are going to have free electrons in them. So conductors are going to conduct electricity because of the presence of free electrons in them. Okay, these free electrons help in the conduction of electricity. See, electricity means transference of charges. Electricity can happen only when charges flow. The charges can be of the form of electrons, or it can be ions. Okay, or it can be ions. So as far as metals are concerned, or as far as very good conductors are concerned, they have a lot of free electrons, going about, playing around. So these free electrons move in a particular situation. When conducive environment is given for these metals, these free electrons start flowing. All right. So these free electrons make it possible for the conductors to conduct electricity. As far as insulators are concerned, there are no free electrons present. Now, electricity is of two types: static electricity and current electricity. What is static electricity? Static, the word means something is at rest. It is not changed. The electric charges which remain at rest. See, we did this experiment of comb, rubbing your comb onto your dry hair, and then attracting it showing it to some paper pieces. No, now we are discussing about the static electricity. Lightning is a very good example of static electricity. Okay, so all these things are happening because the electric charges are at rest. It is just that they are attracting each other. They are not moving. So these kind of electricity, wherein the electric charges remain at rest, this is known as static electricity. What is meant by current electricity? When electric charges are moving, are in motion, we say current electricity is in place. When we generally use the word electricity in this chapter, we are talking about current electricity and not static electricity. Okay, so current electricity is termed as electricity in this particular chapter. So the current that we are using at home is an example of current electricity. Normal electricity, we are talking about current electricity. All right, see, this is what is going to happen. In a metal, if you see, there are a lot of free electrons out here. Okay, the free electrons are going to be in random motion, total random motion. But then when you are placing it in an electric, when you are applying some kind of cell or battery in this particular area, okay, say you have applied a battery, that is, you are creating a potential. That is what we'll be doing, potential. Okay, we will be generating a potential. Then these electrons are going to flow in a particular direction. The electrons are going to flow towards the positive side. I have made this bigger in order to indicate that this is positive and this is negative. The electrons will start flowing towards the positive side. Now, this particular scenario generates electricity. This generates electricity. All right. So generally, if you see, take a normal metal, electrons will be in motion, but it will be in random motion, which in turn cancels out each other. Cancels out, one electron is going to go this way and another electron is going to go in the opposite direction. So that net effect is going to cancel out. Now we are going to deal with electric potential. See, what is meant by electric potential? See, for water to flow from one particular area to another area, water to flow by itself from one particular area to another area, what is required? Some kind of height difference is required. Some kind of height difference is required. For wind to flow from one particular area to another area, what is required? For wind to flow from one area to another area, pressure difference is required. For charges to flow from one particular area to another area, what is required? Potential difference is required. Potential difference is required. Right? So we have two terms like height is there, and height difference is there. Height difference is there. All right. So height is a general term. Height difference is what is required for water to flow. Likewise, potential is there. Okay, we are going to define potential and also potential difference. Potential difference is required for charges to flow. Charges to flow. All right. Now, what is potential? Potential, see, we are talking about an electric field. Okay, we are talking about an electric field. At this particular area, some kind of effect of charge is felt. Okay, electric potential is electric potential at a point. We are talking about the electric potential at this particular point. Okay, at this particular point. What is the electric potential at this particular point? See, I am bringing a unit positive charge, hypothetical unit positive charge. Unit positive charge from infinity to this particular area. From infinity to this particular area, what am I doing? I am bringing a unit positive charge. Now, what is the work done to bring that unit positive charge from infinity to this particular area? This work done is known as electric potential. This is known as electric potential. So what is the work done? So what is potential, electric potential? It is a work done. Work. All right. We have to take care of all these terms. What is electric potential? It is some kind of work. What kind of work? It is a work done to bring unit positive charge from infinity to this particular area. All right, the unit of electric potential is volt. Unit is volt. So we have, how do we define volt? How do we define 1 volt? So we have two terms. What is 1 volt? This is our question. We have two terms, work done and charge. Work done and charge. What is the unit of work? It is 1 joule. What? Say it is joule, and the minimum quantity that we are going to talk about is 1 joule. What is charge? What is charge? Charge is Coulomb. The unit is Coulomb, and we are going to discuss about 1 Coulomb. When we are discussing about 1 volt, what are the terms involved in the definition? We know that there are two terms, work and charge, right? The unit of work is joule and unit of charge is Coulomb. We are going to talk about, since we are talking about 1 volt, we are going to talk about 1 joule and 1 Coulomb. So what is 1 volt? It is a potential of 1 volt at a point. What does it mean? It means that 1 joule of work is done to bring 1 Coulomb of charge from infinity to that particular point. To that particular point. See, from these terms, we can actually derive the particular definition of 1 volt, right? So 1 joule of work is done in order to bring 1 Coulomb of charge to a particular point from infinity. So that work is known as 1 volt. That work is known as 1 volt. A potential at a point is said to be 1 volt. This is a very important question. This particular point is said to be 1 volt when 1 Coulomb of charge is brought in from infinity to this particular point. And the work done is 1 joule for that. Then the potential is going to be 1 volt. Okay. Now coming to potential difference. Okay. Now coming to potential difference. What is potential difference? Now we are going to consider 2 points. The potential difference is the difference of potential between 2 points. That is between these 2 points in simple words. Otherwise, what can you say? The amount of work done in moving charges from one point to another. Amount of work done. Still, the work done term is there and charge term is there. All right, charge term is there. So, amount of work done in moving charges from one point to another. This is known as potential difference. Potential difference is the reason why charges flow. Potential difference is the reason why the charges flow. So we have the mathematical formula of potential difference. See, when you are writing notes, any kind of formula which comes in, any unit which comes in, please do write it behind your book so that it will be easy for you guys to revise. If you mix theory as well as mathematical formula and unit, you will find it very difficult to revise it. Okay, so what you have to do is you have to write electric potential. Say charge. The first thing that we encountered was charge. What is the unit of charge? Unit of charge is Coulomb. This has to be written behind the textbook, no, behind the notebook. What is potential? The unit is going to be volt. Okay, unit is going to be volt. What is potential difference? It is work done by unit type. Work done per charge. That is quantity of charge moved. Quantity of charge moved. This has to be written behind the notebook. Again, potential difference unit is going to be same as that of potential itself, which is volt. Okay, this has to be written behind the notebook. Now, what is the formula of potential difference? See, work done for moving individual charges. Work done for moving charges. Quantity of charge moved. Work done per charge. Work done per means divided by quantity of charge. Quantity of charge. This is potential difference. This is potential difference. Okay, this is a very important formula because there have been quite a few questions on this. Now coming to the SI unit. SI unit of, so P is equal to W by Q. Please write it down behind the notebook. So what is the SI unit? SI unit of potential difference is volt. So now again we are going to define 1 volt based on this. 1 volt. So what is 1 volt? Volt is work by charge. Work by charge, right? So work by charge. Again, the potential difference between 2 points is said to be 1 volt when 1 joule of work is done to move 1 coulomb of charge between them. See, we are using this mathematical formula to define 1 volt. So the potential difference between 2 points is said to be 1 volt when 1 joule of work is done to move 1 coulomb of charge from one point to another. So this is potential difference. Now, how do you measure potential difference? The measurement of potential difference is done using a machine which is voltmeter. This is used to measure. This is the voltmeter. Voltmeter is generally made of high resistance stuff. This has high resistance because when electricity flows through this, we don't want any electric current to enter into this. All right. So there are 2 things. This is of high resistance, and the other point is that the voltmeter is always connected in parallel. This connection is known as parallel connection. Parallel connection. So it is always connected in parallel to the point where the potential difference is supposed to be measured. Okay. Voltmeter has high resistance and is always connected in parallel across the point where potential difference is supposed to be measured. Okay. The next point being the electric current. Electric current, when 2 charge bodies, say 2 charge bodies are there, they are at different potential. So like how we have high difference, we are having electric potential over here. So obviously charges are supposed to be there. Water is supposed to be there so that water can flow. High difference is supposed to be there so that water can flow. Likewise, charged bodies are supposed to be there and they should be at different electric potentials. Now they are connected using an electric, using a metal wire. Say they are connected using a metal wire. Then the charges are going to flow from higher potential to lower potential. Then the charges are going to flow from higher potential to lower potential. This flow is known as, this flow of electrons is known as electric current. All right, the electric current is a flow of electric charges in a conductor. Electric charges may not just be electrons, it can be ions as well, but as far as we are concerned, we are going to stick to the electrons. Electric current is a flow of electric charges in a conductor. So now what is the magnitude of electric current? What is the magnitude of electric current? The amount of electric charge passing through a point, through a given point in a conductor. Say we are standing over here, okay, and we are seeing a lot of cars getting passed. Okay, lot of cars are getting passed like this. Okay, in the road. Now I am watching this particular area. I am watching this particular area. I am counting for 1 minute. In 1 minute, how many cars are passing this particular point? Okay, this is going to give me the rate at which the car is moving. Likewise, I am seeing at this particular, this is a metal wire. Consider this is a metal wire, and electrons are moving. Sorry, electrons are moving. Electrons are going to have negative charge, right? Electrons are moving. So electrons are moving in a very systematic way. I am watching this particular point in the conductor. So the amount of electric charge which is passing through a given point at a given time, or 1 second, in a unit time, we can call that unit time as 1 second. So I am counting how many electrons are passing through this particular point in 1 second. That gives the rate of flow of charges, rate of flow of electric charge. This rate of flow of electric charge is known as current. This rate of flow of electric charge is known as current. So what is current? Current is the rate of flow of electric charge. How do we find that out? We can find that out by observing a point in the conductor for 1 second. And it is not a simple observation. We have to observe how many charges are passing through this point in 1 second. Okay. So it gives the rate of flow of electric charge. So I is going to be number of charges passing per unit time. Number of charges passing per unit time. Again, this is a formula. You are supposed to write it behind your notebook. SI unit is going to be, ladies and gentlemen, ampere. SI unit is going to be ampere. All right. Now, how do we measure electric current okay. Now, first we have to define unit. Whenever we encounter a physical quantity, all these are physical quantity. Voltage is a physical quantity. Current is a physical quantity, or for that matter, distance is a physical quantity. Now, we have come to current, right? Current has, what is its unit? Unit is going to be ampere. Unit is going to be ampere. What is unit of charge? Charge unit is Coulomb. We define unit of charge, which is Coulomb, and we define 1 Coulomb. We define unit of potential, which is volt, and we define 1 volt. We know that the unit of current is ampere. Now we have to define what is 1 ampere. So we denote current using I. Okay. What was the mathematical formula? Charge per time. What is the amount of charge that is flowing in unit time? So what if 1 Coulomb is passing in 1 second? Then we say that the current is 1 ampere. We say that the current is 1 ampere when 1 Coulomb of charge is passing through a point on the conductor in 1 second. In a conductor, when 1 Coulomb of charge is being passed in 1 second through a point, then we say that the current is 1 ampere. There are lesser units, that smaller units of current, which is milliampere, microampere, all those things are there. Milli always deals with 1 by thousands. Micro always deal with 1 by 10 raised to 6. All right. And there are a higher voltage, higher currents as well. We are not going to study all those things. Now, how do we measure current? We measure current using ammeter, the instrument ammeter. Ammeter is always, see, how is it connected? Ammeter is always connected in series with the point where current is supposed to be measured. And ammeter is of very, very less resistance. Very less resistance, because we want all the current to pass through it. We want all the current to pass through it. For that reason, ammeter is of very negligible resistance, and moreover, ammeter is always connected in series to the point where we have to measure the current. All right, ladies and gentlemen. Now, can you take a moment to revise all these things? Okay, now how do we ensure? We saw that the electric charges are going to flow, right? But we have to ensure that there is continuous flow of electric current. So what has to be done is we have to ensure that there is always a potential difference. There is always a potential difference maintained between two ends of a conductor. So this is a conductor. So, okay, my conductor has gone all the way slanting. So this is, 1 second, there is something wrong with the scribbler. So say this is a conductor. I don't know what is wrong. Okay. So I have to ensure that both these ends are at different potential. Okay. In order to ensure that these are at different potential, what should I be doing? We should be actually attaching them to a cell or a battery. Cell or a battery. Now the cell, I don't know what is wrong. Cell or a battery. All right, let me just draw this again. Okay, we have to attach the ends to a cell or a battery. So there will be some chemical reactions happening inside the cell or a battery to ensure that the 2 points between the conductor are going to be kept at different potentials, which will ensure that there is always a flow of current. So the most important point being, how do we ensure continuous flow of electric current? We have to maintain 2 different points at entirely different potentials. There should be potential difference. In order to make sure that continuous potential difference is there, they have to be attached to cell or battery. So how does cell or battery ensure that there is a potential difference? Chemical reactions which are happening inside the cell or battery make sure that both of the locations are at different potentials. Now, what is the direction of electric current? Generally, the direction of electric current is taken from positive to negative. Direction of electric current is from positive to negative. But this is current direction. But direction of movement of electron is always from negative to positive. So we can say that the direction of current is the opposite of movement of the direction of movement of electron. Direction of current is entirely in the opposite way as the direction of movement of electrons. Okay. So now coming again, how does the current flow in a wire? How does this happen? When metal wire is not connected, again the electrons are going to move in an entirely random direction. But when a cell or battery is connected to a wire, so what happens? There is an electric force. This electric force is going to pull all the electrons in the same direction. That is towards the positive side of the battery. Electrons are going to be attracted towards the positive side of the battery. Now, this is what creates this systematic movement of all electrons together in one direction. This is what is going to create an electric flow. Now, what is electric circuit? See the conducting path of the conducting path which has a resistor, which might have a resistor, or which might have a bulb. All these things connected by a switch. Okay, something is seriously wrong. All connected with a switch and battery and cell. This whole conducting path with wires, switch, and maybe a cell or a battery or a bulb, all those things together are known as electric circuit. Now the circuit can be open or closed. What is meant by open? The switch is not connected. What we have to understand is that the whole circuit has to be closed. Otherwise, the water is not going to electrons are not going to flow. That is, the current is not going to flow. In an open circuit, the circuit is broken. That is, the switch is open over here. The switch is open over here. So the current is not going to flow. In this particular case, the current is not going to flow. Okay. So what should we be doing? When the switch is on, that is, the circuit is completed. The circuit is completed. Now the current starts flowing. Okay. There are quite a few symbols you have to learn, but at least go through all these symbols. Okay. These symbols are there. See, this is how the switch is open. This is a symbol of open switch, and this is a symbol of a closed switch. Okay, this is the symbol. This is the rough diagram of a circuit. Now, when somebody asks you to write about a circuit diagram, at least draw this to make sure that the answer is complete. Okay, these are quite a few symbols which has been given. what you have to understand is that voltmeter also has a positive and negative side. Yeah, ammeter also has a positive and negative side. Positive is supposed to be connected to the positive of the battery. Okay, when you are drawing that, you have to draw positive and negative, positive and negative. When you are drawing for rheostat, this particular signal, which is an arrow crossing the resistor, should be there. Should be there. Okay, this particular symbols mean the wires are like this. They are not joined. It is simply like this. They have not cut across. They are not joined at any particular location. Okay, this is an open switch without a dot. This is open switch. Okay, this is a closed switch. Please do go through all these symbols in case they ask something on using this particular diagram. They'll be using problems. They'll be giving us problems. So go through all the symbols and understand it and learn. Okay, we can create variable resistances in a circuit using an instrument known as rheostat. Okay, now coming to Ohm's law. This is also one very important law. Please do learn Ohm's law by heart, because in every question paper, almost every question paper, you can see either Ohm's law or the experiment of Ohm's law or the formula of Ohm's law. Okay, so what is Ohm's law? Now we have studied two physical quantities, right? Voltage and current. We have studied two quantities, voltage and current. How are they related to each other? See, at constant temperature, we are not going to change the temperature. At constant temperature, the current through a conductor. Now, current is going through the conductor. This is going to be proportional. This is going to be directly proportional to the voltage across the conductor. At a constant temperature, the current flowing through a conductor is directly proportional to the potential difference across its edge. Okay, very, very, very important statement. The current through a conductor is going to be directly proportional to the voltage across the conductor as long as temperature is constant. Temperature is constant. Okay, so this is very important formula. Kindly write the formula behind your notebook. Okay. So this is rheostat. Okay, this can create variable resistance in a circuit. Okay. Now coming again, we can also write I is proportional to B as B is also proportional to I, which gives, in order to change the sign of proportionality, we are supposed to bring in a constant. That constant is going to be R, which is the resistance. This is the resistance. Okay. So what is resistance? R is equal to V by I. I can also write R is equal to V by I. So what is resistance? Resistance, one of the definition is the ratio between the potential to the current. Ratio between the potentials applied between the ends of a conductor to the current flowing through it. That is resistance. Okay. The ratio between the potentials applied across a conductor to the current flowing through the conductor. This is ratio, right? Across a conductor. This is known as resistance. So from Ohm's law, we can define resistance. Ohm's law is extremely important. There will be quite a few questions based on this. Now, we can also understand that current is proportional to potential difference, and current is inversely proportional to resistance. When resistance increases, resistance to the flow of current increases, current is going to decrease. Okay, these are important conclusions. Now, these kind of questions, potential difference across a conductor is doubled. Find what is going to happen to the current. These kind of questions are very important. So what is going to happen? V is equal to IR. V is equal to IR. Now, potential difference across a conductor is doubled. What is going to happen to the current? What you have to understand, we are talking about the current. First, derive the formula of current from this. I is equal to V by R. This is the first case. Now, what happened, ladies and gentlemen? The current is changing somehow. How did the current change? My voltage has become 2 times. 2 times. Okay, 2 times the original voltage. So, 2 into V by R. 2 into V by R. That means I can write V by R as I1. So 2 times. My current has become 2 times. My current has become 2 times. All these things, all these kind of questions. Say what is going to happen to the current when your voltage is reduced to half. So I1 is going to be V by R. Now my voltage is reduced by half. Voltage is reduced by V by 2. Voltage has become V by 2. Now my R is also here. So what can I do? I can take this 2 outside and write this as V by R. What is V by R? It is I1. So my current has reduced half the time. Okay, my current has halved. That is how we can derive at this particular conclusion. All right. So these kind of questions are very important. Now we are going on to the next physical quantity, which is the resistance. We have studied about voltage. We have studied about current. Now we are moving on to the resistance. Ohm's law is also very, very important. What is resistance? See, it is a property of a conductor. What is the speciality of that property? Because of this property, the conductor is going to oppose the flow of the current. This particular property is known as resistance. Okay, when electrons are going to move from one end to another end, these electrons are going to collide and collide. They are going to collide with other electrons. They are going to collide with other atoms. They are going to collide with ions, which are present throughout the body of the conductor. These collisions are the reason for resistance along the conductor. Okay. So now the resistance is going to be numerically equal to, there should be a number. How can you derive resistance? It is equal to the ratio between voltage and current. It is as simple as that. Why does resistance happen? Because of the collision of the electrons, free moving electrons to other electrons and ions and atoms. Okay. Now the resistance, ladies and gentlemen, these are very important questions. Please write it down on the back side of your notebook. Resistance of a conductor is going to depend on the length of a conductor. Length of a conductor. Thickness of a conductor. One conductor is very small. The other conductor is gundu, very, 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 very thick. Okay, that is going to depend on the thickness of the conductor. Nature of the material of the conductor. So how is it going to be like? It is going to be like a car encountering traffic block along the road. Okay. Say if the road is of high length, of a great length. Okay. Say another road is of small length. See, the chances that the car encounters other car is more in a lengthier pathway. Is it right or wrong? He is going to encounter more traffic as he is going to have to travel a long distance. So when length increases, resistance increases. Are you guys clear with this? Okay. Now the second thing is that, say there is a narrow road. Say the other road is going to be very wide. Say this is the other road. See, the chances that the car encounters traffic is more in the narrow road, right? When thickness increases, the chances that he encounters traffic is less. Chances that the resistance happen is less. So when thickness, area increases, area of cross section is related to thickness. Cross section increases, resistance decreases, because the car encounters less traffic in this particular area. Now, what about the nature of the road? One road is very bumpy and has a lot of potholes. Other road is NH road and it is fully tarred and very rubberized road. Chances that he encounters non-smooth resistance is very less in the NH road. National highway. Is it right or wrong? So the nature of material is also going to affect the resistance of a conductor. Okay. So when length increases, resistance decreases. When area of cross section, see, this is how resistance comes. Okay. So when electrons move around, it goes and encounters different atoms, different other electrons. But then this is comparatively smooth and this is comparatively complicated. This has higher resistance. This has less resistance. Now coming to when length increases, resistance decrease. Resistance is going to increase. Area of cross section increases, resistance is going to decrease. When temperature increases, as far as metals are concerned, for metals, when temperature increases, resistance increases. SI unit of resistance. is ohm. Please write it on the back side. Please write on back side that length, thickness, as well as nature of material and temperature is going to affect resistance. Okay, SI unit is going to be ohm. So what is 1 ohm? When we say about some kind of unit, we have to define the define unit of that as well, which is 1 ohm. What is 1 ohm? Say resistance. What is the mathematical formula of resistance? R is equal to V by I. V by I. So 1 ohm is the resistance of a conductor if the current passing through the conductor is 1 ampere when a voltage of 1 volt is applied across it. Say there is a conductor and a potential difference of 1 volt is existing between 2 points of the conductor, and the current passing through that is 1 ampere. Then the resistance is 1 ohm. Say a potential difference of 1 volt is applied between the ends of a conductor, and this has caused a current of 1 ampere to pass through it. Then the resistance is said to be 1 ohm. Okay. Now coming to the graph between V and I. We take the x-axis as voltage and y-axis as I. Okay. Now what is going to happen? Now if we actually map the relationship between voltage and current, this is the experiment to do that. Okay, so we have put a battery over here, we have put a switch over here, we have a meter to actually measure the current and voltmeter to actually measure the voltage. If you see, ammeter's positive is related to the battery's positive, ammeter's negative is related to the battery's negative, and so is the case with the voltmeter. Now this is the resistance and this is the rheostat. We are going to measure the voltage against this particular resistance. Now, rheostat is adjusted in such a way that only very little current passes through it. Only very little current. So that means a high resistance is kept with the help of rheostat. Now, the current is measured using a meter and voltage is measured using a voltmeter. Now, the rheostat is adjusted so that a bit more I1 is measured and another current measures through this. So now again measure the current and measure the voltage. Another current is created, which is I3 with the help of rheostat by adjusting the rheostat. Now in all these cases, V1, V2, V3 is also measured. When you map it out, inevitably you are going to get a straight line, inclined straight line, which shows that voltage and current are proportional to each other. Voltage and current are proportional to each other. And if you do V1 by I1, that is going to be equal to V2 by I2, which is again going to be equal to V3 by I3, which is going to be the resistance. This is going to be the resistance of the conductor. This is going to be the resistance of the conductor. So this is a very important experiment, and you have to learn the graph as well. Now, what are good conductors, resistors, and insulators? Good conductors, now we are going to define the same thing using resistance. Okay, now what are good conductors? The substances, the electrical conductors with very less resistance, least resistance, okay, least electrical resistance are known as good conductors. They are going to allow the electricity to pass very smoothly through them. Okay, silver is going to be the best conductor. Copper and aluminum are also good conductors. So if you see, the electric wires are generally made using copper or aluminum. Why is that so? In spite of aluminum being a very good conductor, aluminum is very costly. No, in spite of silver being the best conductor, silver is very, very costly. So we use the second best, which is copper and aluminum. They are also equally good conductors. Now, what are resistors? Resistors are those substances with high electrical resistance. Okay, alloys like nichrome, constantan are very good resistors. They are used as heating elements in iron boxes. Now, what about insulators? Substances with infinitely high electrical resistance. They do not allow electricity to pass through them. Rubber is a very good example. And using rubber, what do? We actually make hand gloves so that we can work on the electrical equipment so that the shock is prevented. Plastic is also a very good insulator. Now, what are the factors which are affecting resistance? We already discussed this. Resistance is directly proportional to the length. Area of cross section is going to affect the resistance in such a way that resistance decreases with area of cross section. When area of cross section is more, resistance is less. When area of cross section is less, the thickness of the road is less. The chances that you encounter traffic is very high. That means resistance and area of cross section are inversely proportional to each other. Now, effect of material. How does the material affect? Say for copper is there. Okay. Nichrome is also made up of copper, but nichrome is an alloy of copper. Okay. So, if you see, no, nichrome is not an alloy of copper. If you see copper and nichrome, okay, say you have taken equal length of copper and nichrome. You have taken equal length and equal diameter. But then the resistance of nichrome is almost 60 times as that of copper. 60 times as that of copper. See, nichrome is a different material and copper is a different material. See how material is going to affect the resistance of different conductors. Now coming to the effect of temperature. If you see pure metals, the resistance is going to increase. Resistance is going to increase when you increase the temperature. Okay. Resistances of alloys like manganese, constantan and nichrome are going to be unaffected with the temperature, unaffected by the temperature. Now, what is the mathematical formula of resistance? R, we already told that it is proportional to length. R, we already told that it is inversely proportional to area. So, clubbing this, temperature has nothing to do with this formula and nature has something to do. We are going to change the inverse, proportional sign with the constant, which is rho. R is equal to rho into L by A. Okay, rho has something to do with the nature of the conductor. Rho is known as resistivity. This constant is known as resistivity. Can you take a minute to revise all these things, please? Okay, let's continue. So we already saw that R is equal to rho into L by A. What is rho? Rho is resistivity. Resistivity is also known as specific resistance. So the same kind of questions. What is going to happen to the resistance when length is doubled, area is doubled, area is 1/3? All these things are going to come. Okay. So now what about the nature of the material? The resistance is also going to depend on the nature of the material. We saw the example of copper and nichrome. Nichrome is an alloy. Okay. Nichrome is an alloy. Some have high resistance and some have less resistance. Now we are going to deal with, okay, so we are going to deal with resistivity. Okay, we are going to deal with resistivity. What is resistivity? See, if you see the formula, R is equal to rho into L by A. From this, what is rho? Rho is equal to R into A divided by L. Divided by L. Okay. Now, so rho is equal to R into A by L. Okay. Now, if you take a conductor with area of cross section as 1 meter square and length as 1 meter. Say I am taking a conductor with area of cross section as 1 meter square and length as 1 meter. Then my specific resistance is equal to my resistance. So my resistivity or specific resistance of a substance is the resistance of the substance when the conductor is taken with area of cross section as 1 meter square and the length as 1 meter. So what is resistivity of a conductor? Resistivity of a conductor is same as resistance. When it is numerically equal to the resistance, when the rod of a substance is of 1 meter long and 1 meter square in cross section. 1 meter square in cross section. The resistivity of a substance is numerically equal to the resistance of a rod of substance which is 1 meter long and 1 meter square in cross section. So how do you come to the unit of resistivity? Rho is equal to R into A by L, which is, if you look at the units, R has a unit of ohm, area has a unit of meter square, length has a unit of meter. Meter and meter square is, it goes and the unit comes to ohm meter. Ohm meter. So this is resistivity has a unit of ohm meter. Okay. So now coming to the next one. Resistivity, very, very important. Resistivity does not depend on the length or thickness. Resistivity does not depend on the length. Please write it on the back side of your notebook. It depends only and only on the nature of the substance and temperature. only on the nature of substance and temperature. What is meant by resistivity of a copper is 1.69 into 10 raised to minus 8. What does it mean? It means that rho is given as 1.69 into 10 raised to minus 8 ohm meter. What does this statement exactly mean? It means that when a copper rod is taken, which is of length 1 meter and has a cross section of 1 meter square, the resistance is going to be equal to this. The resistance is going to be equal to this. What is meant by the fact that the resistivity of silver is least? It means that silver offers least resistance for the flow of current. Okay, silver is the best conductor of electricity. Silver has least resistance. Still, why are electric wires not made with silver? Because silver is very expensive. Copper and aluminum are the next best alternative as far as price is concerned and conduction is concerned. Now, compare the resistivity of alloys and metals. Alloys are going to have higher resistance than metals. Say, for example, manganese is there. Okay, manganese is made up of copper, manganese, nickel. Okay, copper, manganese, nickel. It is 25 times more resistant than copper. See, copper is part of this. In spite of that, manganese is going to be 25 times more resistant than copper. Constantan, if you see, it is going to be made up of copper and nickel. Now it is 30 times more resistant than copper. Okay. Now if you see nichrome, it is made up of nickel, chromium, and manganese. Okay. This is going to be 60 times more resistant than copper. Now, so if you understand, the alloys are going to have higher resistance than pure metal, and they are not affected by temperature as well. Now, why are heating elements made up of alloys like nichrome? This is a very important question. Now, the substances like nichrome, they are going to have high resistivity, which means they are going to produce a lot of heat. They are going to produce a lot of heat. So, heat is required for our equipment like iron box. Heat is required. So, they are very advantageous. And moreover, the general trend is that when you heat a substance, it generally and readily reacts with oxygen. So if something reacts with oxygen, that substance is going to be destroyed. But substances like nichrome, if you see, they do not undergo oxidation. That is reaction with oxygen, even at higher temperature. So they are very advantageous. They are not destroyed with higher temperature. Moreover, they have high melting point. Generally, in case of copper and all, if you actually heat it, they get melted at a particular point and they break, right? So, but substances like nichrome have high melting point and they do not melt at higher temperatures. And nichrome wire can be kept red hot without burning in air, which is also highly advantageous. So this particular question is very important, ladies and gentlemen. Why are heating elements made up of nichrome? They have high resistivity, they produce a lot of heat, they do not undergo oxidation even at higher temperature, they have high melting point, and they can be kept red hot without burning in air. Now, what about semiconductors? Semiconductors are those substances like silicon and germanium. Their conductivity or resistivity is in between that of conductor and insulator. They have their resistivity in between that of conductors and insulators. The resistivity of conductor, unlike metals, in metals what happened? Resistance increases with temperature. But as far as semiconductors are concerned, resistivity is going to decrease with temperature. So the resistivity of semiconductors are generally affected by the temperature as well as impurity concentration. We actually induce some kind of impurity. Based on that, with impurities, their conduction is going to change. Okay, they are generally used to make solar cells, transistors, etc. Okay, so this is regarding the resistivity. Can you take a moment to revise? So let's continue. Now we are going to deal with the combination of resistors. There are two ways in which the resistors can be combined. One is a series connection and another is the parallel connection, which is also widely used in domestic circuit. So what about this series connection? Say this is R1 and this is R2. All right. and say this is R1 and this is R2. So as far as series is concerned, this is back-to-back connection. They are connected back-to-back. And in parallel connection, they are connected from the same point. From this point itself, they are connected, right? So they are connected across the same point. This is parallel connection. Now, if you see series connection, R is equal to the effective resistance is going to be the sum of two, R1 plus R2. Whereas in parallel connection, there are two steps for deriving this. Parallel connection is going to be equal to 1 by R1 plus 1 by R2. All right, which is equal to Rp is going to be equal to R1 R2 divided by R1 plus R2. R1 plus R2. All right. So parallel connection effective resistance is there, and series connection also has got a different effective resistance. Okay, so for series connection it is summation of all the resistance, and for parallel connection it is quite different. There are two steps involved. One is 1 by Rp is equal to 1 by R1 plus 1 by R2. You have to solve it and invert it in order to get the right answer. Now for series connection, it is like a water flow. Okay, it is like a water flow. So how do you do that? Say water has started from this point, started flowing through this point. The water which is experienced over here, the quantity of water is going to be same here and here. Water is equal to current. Water is equal to current. So the current is going to be same. Current across the two resistance is going to be same. In this particular case, if you see, okay, I'll just clear this off. In parallel resistance, if you see, what is going to happen? See, this is parallel resistance. Okay. So now what is going to happen? The water has started flowing from here. It encounters two paths. Now the water is going to split. Water is going to split. If it is wider, you can encounter more water over here. If this is lesser, you encounter less water over here. Now in parallel, in series, what happens? Series, current is same. Current is same. In parallel, what is going to happen? In parallel, current is different. Current is equal to water. Water and current is going to be synonyms. Okay. Now what about if current is same, then the voltage is different across the resistance. When current is same, voltage is going to be different. This is going to have V1 and this is going to have V2. And when current is different, voltage is going to be same. V is going to be same as that of the battery. V is going to be same. Okay, in this particular case, in series, the resistance is more. Effective resistance is more. Effective resistance is higher. Say this is R and this is R. Okay, this is R. The effective resistance is going to be 2R in this particular case. Say this is R and this is R. The effective resistance is going to be R by 2 in this case. The effective resistance decreases in this particular case. And moreover, the most important thing in this particular case, in series, one switch controls the entire flow of current. Only we cannot have individual switches for this resistance and this resistance. Only one switch is possible. Okay. In this particular case, what can you do? In this case, you can have individual switches to control the individual switches to control the flow of current through different conductors. Okay, so here individual switch is not possible. Individual switch not possible. Switch is not possible. And in this particular case, individual switch is possible. The resistors can be controlled using individual switches possible. Okay, all right. So these are the major important differences between series and parallel. So RS is going to be effective resistance is going to be R1 plus R2 plus R3. In case of parallel, it is going to be 1 by R3 is equal to 1 by R1 plus 1 by R2 plus 1 by R3. And current is going to be same as far as series is concerned. Please remember the water flow. Okay, current is going to be different in case of parallel. If current is same, then voltage is going to be different. If current is different, then voltage is going to be same. Equivalent resistance is high, equivalent resistance is low in this case. Possible to have only one switch. It can be controlled using individual switches. So this is the story of combination. Now one point that I left out is, see, this is the series, okay? This is a series connection. Only one switch, say any of this, consider this particular thing has broken. What is going to happen? The entire bulb series is going to go off. go off. Even if one of them has disconnected, then the entire series is going to switch off. There was a film like this. They were planning to have some New Year ball is there. Okay, it has about 10,000 small serial bulbs in that. One of the bulb blew off. Then they have to find it and fix it before midnight. So this was the theme of the story. In any case, it will be extremely difficult. We don't know which one went off, right? So it will be extremely difficult to do this. The whole thing is controlled by one particular switch, Whereas in case of parallel, individual, see, in case this is off and this is on. Okay, this is on. Consider this is on. So what, and this is also off. What will happen? What will happen if current is going to pass through this? Current goes and encounters that this is off. It will not go through this path, but then current encounters that this is on. So it is very happy and goes through this path and completes its circuit. Okay, so this is what is going to happen. I'm coming to the resistance and resistivity. See, what is resistance? Resistance is the property of a conductor which resists the flow of charges. What is resistivity? Resistance per unit length of a unit length and unit cross section of a material. This is same as resistance, but per unit length and per unit cross section of a material. Okay, that is resistivity. The unit of resistance is ohm, unit of resistivity is ohm meter. Resistance is going to depend on length, cross section, material, and temperature. Whereas resistivity does not depend on length and area. It depends only on the temperature and the nature of material. Okay, the difference is also very important. Now, which one is preferable in domestic wiring? Is series preferable or is parallel preferable? Okay, see, series connection, the effective resistance is going to be more, so it is not preferred. Series connection, your fan, your heater, your AC, and your washing machine, consider that they are in series. One switch, if you switch it on, your fan, your washing machine, your AC, and everything is going to go on. Okay, it is not advisable. So they cannot be controlled by individual switches. So you're not going to use series connection, except in one case that we'll discuss. Okay, except in fact 2 cases that we are going to discuss. So another thing is that we already told that the voltage is going to be different in series, right? Individual people are going to have different voltages. See, every appliance need to have a specific voltage in order to work at its best. Okay, say in series, the voltage is going to be split across. They are going to have different voltages. So it is not advisable to have series because every appliance is made to work in 220 volts. 220 volt, the same as that in the power line. But if you're connecting it in series, then that is going to affect the voltage. Okay. So series connection, the overall resistance is also going to go up. So the current is going to, because of which a large amount of heat, large amount of current is going to be wasted as heat. And ultimately, these things will not work properly. All the appliances are not going to work properly. Whereas if you're going to use parallel connection, then even if one of the appliance stops working, say your fan stops working, it is not going to affect your washing machine because they are in parallel connection. See, this is your fan, and this is your washing machine, and this is your AC. Okay, they are connected to the power line. All right, no, okay. This is your AC. They are connected in it. So even if this does not work, this will work properly. And they can be connected using individual switches. Okay. And moreover, the effective resistance is very low because we are having parallel connection. That is also advantageous. They are going to experience the same voltage of 220 volt across all the appliances because this is a parallel connection. So in general, parallel connection is very much advisable as far as domestic circuit is concerned, except in 2 places where this is going to happen in series. One is the master switch connection, which is going to control all the equipments together. And the another very important place where series connection is used is fuse. We are going to have a fuse over here. Say we are going to have a fuse over here. This is a fuse box. Okay. In fuse box, what happens? Generally, we take a copper one. Okay. Generally, we are going to have a copper wire over here of comparatively high resistance. When a lot of current flows through this, when accidentally some overloading happens, say when overloading happens or short circuiting happens, in these two scenarios, tremendous current is going to pass through this. Tremendous current is going to pass through this. Then what is going to happen if tremendous current is going to pass through this? These equipments are going to get destroyed. These equipments are going to get destroyed. So these equipments are supposed to be saved. All equipments are supposed to be saved. Now, when tremendous current passes through this copper wire has comparatively higher resistance. So this is going to create more heat. When more heat is created, because when it reaches a melting point, this melts. This particular wire is going to melt. And then what happens? This melts and breaks the circuit. Okay, breaks the circuit. And the entire current flow is disrupted. Thus, all the equipments are saved. So, as far as fuse is concerned, fuse wire is kept in series with all the appliances. Okay, this is also a very important question. We have to describe the working of fuse as well. Now, what is electric power? Can you take a moment to revise? So let's continue. What is electric power? So electric power is the work done per unit time. Electric power is the electric work done. Any power, if you ask two people to actually, keep one brick above the other, keep 100 bricks one above the other. One person does the work in 5 minutes, the other person say he has done it in 10 minutes. You say that he is more energetic. Why? He has done the work in lesser amount of time. In 5 minutes, one person did it, the other person did it in 10 minutes. So you say that this particular person has higher rate of working because he took lesser time to do the same work. So the same concept is applicable for electricity as well. Electric power means the work done per unit time. Okay, we can also write this as energy consumed. Work is always same as energy, except for the wastage of energy. Energy consumed per unit time. So power is equal to energy consumed or work done per unit time. So the unit of power is going to be watts, W-A-T-T. Okay, watts. So now you have to define 1 watt. What is 1 watt? See, you have to start from the mathematical formula. Work done by time. Okay, what is the unit of work? It is going to be joule. As I already told you, energy and work is kind of synonym of each other. Okay, the unit of energy is joule, unit of work is also joule. Okay, so if 1 joule of work is done in 1 second, then we say the power is 1 watt. If 1 joule of work is done in 1 second, then we say that the power is 1 watt. We have higher powers, higher units of power, which is kilowatt. The word kilo always means 1000. Kilo always means 1000 normal unit, which is 1000 watts. Okay, so 1 kilowatt is equal to 1000 watts. Now, power voltage rating in an appliance. What is meant by power voltage rating in an appliance? If you take some appliance like heater or AC, we can see a marking which is 100 watt, 220 volt. What is meant by that? It means that the appliance is going to work best in 220 volt, and the power consumption is going to be 100 watt. It means that the appliance is going to have a power consumption of 100 watt, which means it is going to consume 100 joules of electric current in 1 second. It means that it is going to consume 100 joules of electric current in 1 second. It also means that what does 220 volt mean? It means that it works best in a voltage of 220 volt. What does the power rating of an electric appliance tells us? It tells us power rating means the rate at which the electrical energy is consumed. Power is equal to work done by time. Power can also be written as energy consumed by time, right? So this also means that 100 watt means that energy of 100 joule is consumed per second. Okay, this is what power is about. Now, what is the formula of calculating power? It is work done by time. You can also write it as energy consumed by time. Now, what are the formula for work? It is VIT. Work. The formula for work is VIT, I square RT or V square by RT. V square by RT. The same can be applied for energy, like heat energy. Heat energy, if you see, heat energy produced by current, if you see, we can use the same formula. Heat energy produced by current can be derived using the same formula, same three formula. It can be VIT, it can be I square RT, or it can be V square by R into T. So this is work. This is work. We are going to discuss the power, right? So power or work or energy has three formula. What are they? Please write it behind your notebook. I square RT, V square by R, and VIT. Okay, there are three formulas. Now, what about power? Power is equal to work by time. So this divided by time. What will be the answer? I square RT divided by T, which is I square R. What will be the next one? This is V square by RT. If you divide T to that is going to be V square by R. Now, if you cut off T from that, this is going to be VI. Okay, we have three formulas for power. This is also very important when it comes to problems. Okay, so power is equal to VI, power is equal to V square by R, and power is also equal to I square R. Now, this is the formula. Now, what is the formula of calculating energy from that? From this, see, as I already told you, power is equal to work or energy by time. Energy by time, right? So, what is energy? Energy is equal to power into time. Power into time. Okay. Now, if you see something like watt hour, okay, this is a unit of energy and not power. So don't get confused when you see the word watt over here. See, this is the power. Unit of power is going to be watt. The unit of time is hour. So if you multiply them, you are going to get energy. The unit of energy can also be watt hour. The unit of energy can also be watt hour. There are quite a few questions, problems based on this. Now, what is the question over here? What does electrical energy consumed by electrical appliance depend on? So, given an appliance, okay, how much electricity does that appliance consume? It depends on power rating of the appliance and time for which the appliance is used. So, how can you say that? We just now derived that energy is equal to power into time, right? So the energy is going to depend on the power rating as well as the time for which it is going to be consumed. Okay. Now, what is 1 watt hour? 1 watt hour. This is the unit. This is the unit of energy, right? This is a unit of energy. This means that 1 watt hour means that the amount of electrical energy consumed by an appliance which has a power rating of 1 watt when it is used for 1 hour. Okay, what is 1 watt hour? The energy consumed by an appliance with a power rating of 1 watt when it is used for 1 hour. That energy is known as 1 watt hour. Okay, we have commercial units of energy as well. What is a commercial unit of energy? 1 kilowatt hour is a commercial unit of energy. We generally call that as 1 unit. 1 unit. 1 kilowatt hour. Kilowatt hour is a commercial unit of electrical energy. We generally call 1 kilowatt hour as 1 unit. So we say our electric consumption came to be 3,000 units or 2,000 units or 1,000 units. Okay, that is that. What does it mean? It means that we have consumed 3,000 kilowatt hours of energy. So what is 1 kilowatt hour in terms of joule? See what all did we discuss? We discussed that the unit of energy can be joule. It can also be kilowatt hour. This is the domestic unit that we normally use. So now we are going to see what is the relationship between kilowatt hour and joule. So how can we derive that? 1 kilowatt hour. 1 kilowatt hour. All right. Now, what is meant by joule? Joule is a SI unit. That means everything should be in SI. This is not in SI and this is not in SI. Kilowatt. What kilowatt is the unit of power? All right. And hour is the unit of time. Now, if you see, in order to convert them to joule, this has to be in SI unit and this also has to be in SI unit. So what is the SI unit of kilowatt? It is watt. Now I am going to convert it into watts. That is 1 kilowatt is 1000 watt. I am also going to convert hour to second, which is the SI unit of time. So what is 1 hour in terms of seconds? It is 60 into 60 seconds. 60 into 60 seconds, which is 36 into 10 raised to 1, 2, 3, 4, 5. 10 raised to 5 watt second, which is 3.6 into 10 raised to 6 joules. Joules. This is how you convert between them. Okay. Can you take a moment to revise this? Okay. So what is 1 unit? 1 unit is the commercial unit. This is a commercial unit of electricity which we generally use to measure at our home or commercial unit. Okay. 1 unit is 1 kilowatt hour. 1 unit is what? Kilowatt hour. 1 unit is the amount of current for which the electric supply department actually charges us. We use, if you have consumed 1000 units, this is what the electricity department is going to charge us for. This is equal to 1 kilowatt hour. All right. This is a unit of energy. Energy. What are some important effects of electric current? Important effects of electric current are heating effect, magnetic effect, chemical effect, etc. Now, what is meant by heating effect of electric current? As we already discussed, when current is going to flow through high resistance wire, say the current is going to flow through a high resistance wire. There, because of the resistance of the wire, heat is going to be produced. This particular heat can be positive or negative. Positive in the sense this can be used in some appliance like bulbs, or it can be used in it is not used in bulbs. It can be used in equipments like heaters or iron box, etc. What is the negative effect? If you are going to use a conductor inside a bulb, what is going to happen? We are expecting light to come out, but major part of the electricity is consumed as heat, which is disadvantageous. So the heating effect of the current can be used for positive as well as negative stuff. Okay. Now, how do you calculate the work done by a current when it is passing through a resistance for time t? See, work done is equal to another formula is there, which is Q into V. Q into V. We are going to derive from this I square RT. Okay. Now, what is Q? Q is equal to, see, if you see current, what is current? Current is equal to Q by T, right? So, Q is going to be I into T. So, I have put I into T instead of Q. Okay, I into T. Now, so W is equal to, instead of Q, I put I into T and this V over here. So, the formula is VIT. You can substitute Ohm's law instead of V. Then it will come to I square RT. Okay, use again, instead of R, if you put, instead of I, if you put V by R, then you will get V squared by R. That is how you derive different formulas. Derivation is not that important. We have already seen the formula of work as well as energy. You remember the three formulas that we wrote: work and energy. The same heat energy can be written as I square RT, V square by RT at VIT. All right. This is what we are talking about. Okay, now coming again, what is Joule's law of heating? According to Joule's law of heating, the heat energy produced is proportional to the square of current, proportional to the resistance of the wire, and the time for which the current is going to pass. That is I square RT. The heat produced, this is very important. This is very important. According to Joule's law, the heating effect is going to be, heating effect produced by the current in a wire is going to be directly proportional to the square of current, proportional to the resistance, and proportional to the time for which the current is going to pass. Again, the same thing. Whenever such a formula is there, they are going to ask you what is going to happen when current is doubled. Can you try that out? What is going to happen when current is doubled? Try it out. Okay, what happens? H is equal to I square RT. Okay, H1 is equal to I square RT. What about the new heat when the current is doubled? 2I the whole square into R into T. What happens? 2 becomes 4. 4I square RT. Now what about this? This is 4 into H1. The heat becomes 4 times. So such questions are very, very important, ladies and gentlemen. Okay, now what is going to happen? Will two wires connected in series or parallel produce more heat? See, obviously in series, what is going to happen? Effective resistance is going to go up. See, heat is directly proportional to resistance. Heat is directly proportional to resistance. So in series, what is going to happen? Resistance is going to go up. So obviously, the heat is going to be more. As far as parallel is concerned, the effective resistance is going to come down. Come down. So the heat produced will be comparatively less. Now, another question. Why does electric fan become warm? Because most of the energy is going to be converted into, even when most of the energy is going to be converted into mechanical energy of rotation, some part is going to be get converted into heat energy because of the resistance. Okay, so if it is run for a long time, because of I square RT, because of the factor of time, it gets heated up. Okay, now what is the property of the current which is used in working toasters and oven? Heating property is used. Okay, now the next question is, what is used to make heaters and all those things? Heating appliances. Nichrome is used. We already discussed the reason. What is made use of to make electric bulb, and why? Tungsten is made use of in making electric bulb. Tungsten. Okay, why? Tungsten has high resistance, because of which when electricity is passed, this glows white. This glows in this has a white glow. Okay, and moreover, this has high melting point. It does not melt and break off easily. And moreover, this is very flexible. This is very flexible, so it can make thin filaments, extremely thin filaments. And this has low rate of evaporation. This has very less. This does not evaporate easily, because of which tungsten is generally preferred as a filament inside the electric bulb. Okay, how is the electric bulb? How does the electric bulb work? When current passes through the thin filament of tungsten, tungsten gets heated up, and because of which it becomes white hot and starts emitting light. But the disadvantage is that a lot of energy is wasted off as heat energy. Now, another thing which is there is the electric bulb is generally filled with inert gases. Okay, generally filled with inert gases. Okay, so what are the inert gases? Argon or nitrogen, etc. Why is that so? Because if air is present, when tungsten gets heated up, it will start reacting with oxygen, and the tungsten burns up easily and it breaks. Okay, so if you fill it with nitrogen and inert gases, it prolongs the age of tungsten. It prolongs the life of tungsten, because of which these inert gases are filled inside the bulb. Okay, coming to the next. I think, yeah, so why is it advisable to use tube lights? Because it is more energy efficient. In tungsten, major energy is going to be wasted off as heat energy. We already discussed about fuse. Fuse is for the protection of our electrical appliances. Fuse wire is generally made up of copper wire, and it has comparatively higher resistance and lesser melting point. Why is that so? Fuse has to protect all the equipment. So when more current flows because of overloading or short circuit, the more heat has to be produced inside the copper wire, and because of which it should melt and it should break the circuit. For this, fuse should be of lower melting point and it should have comparatively higher resistance. It should be it should be aligned in such a way that the maximum current which is required by all the appliance should be calculated, and accordingly the thickness and the length of the copper wire should be decided. The fuse wire should be decided. The fuse is generally connected in series with all the electrical appliances. I think that's it, ladies and gentlemen. We have not discussed any of the questions from this chapter. We'll be doing it sometime next week. Okay, that's all. Thank you all.